So when you look at this exercise, you'll notice in the carbon chain that there's a double bond. And that double bond is a sign that you'll be doing an addition reaction here. That extra bond, those extra electrons in the pi bond, are like extra molecular glue that you can use to add things onto this carbon chain. What you're adding depends on the rest of what you're mixing with that carbon chain. Here you'll notice that you have two separate steps, and in the first step you're adding borane that's stabilized by tetrahydrofuran, or THF. That's in one step. Subsequent to that, you're adding hydrogen peroxide and sodium hydroxide. And when you see all of those ingredients, what you should think of is hydroboration-oxidation. So you would want to know the reaction well enough that when you see those reagents, you think that, oh, this is hydroboration-oxidation. Specifically, when you have hydroboration-oxidation, you want to know what you're adding, where you're adding it, and how you're adding it. What direction is it being added from? Now, with hydroboration-oxidation, you're adding a hydrogen and an OH, H and OH. You're adding those in an anti-Markovnikov way. That means that the hydrogen will go on the more substituted carbon. It's anti-Markovnikov. There's also no rearrangement with this reaction, so you don't have to worry about that. The only two carbons that are going to have things added onto them are the two carbons in the double bond in hydroboration-oxidation. Finally, this is syn addition. That means that both the hydrogen and the oxygen will be coming towards us, or both the hydrogen and the oxygen will be going away from us. But they will be on the same side as each other. They'll be syn. So for this particular reaction, you would look at this carbon chain, and you'd specifically look at the two carbons in the double bond. So because this is anti-Markovnikov, the hydrogen is going to go on the more substituted of those carbons. Now the carbon in the middle is bonded to two other carbons, so it is secondary. And the carbon on the end is only bonded to one other carbon, so it is primary. The hydrogen in this anti-Markovnikov reaction goes on the more substituted carbon, and so the hydrogen will go on this secondary carbon here. And to stick it on there, we're going to use the pi electrons, so that pi bond isn't going to be there anymore. That leaves us just one place for the OH to add. That's on the end, on the other carbon that was involved in the double bond. And so we'll add our OH there. And in this case, we don't have any chiral centers. We don't have any chiral centers, and these aren't being added to a ring. So you don't have to indicate the three-dimensional arrangement of these bonds. It doesn't make a difference. But if you did have a chiral center, you would want to draw each of those bonds as being cis, so both coming out at you or both going away. And because your starting material is flat, the reaction can happen with equal probability on either side. So if you did have a chiral center, you would want to draw both enantiomers, because you'll have a racemic mixture, a 50-50 mixture of both enantiomers. In this case, we don't have a chiral center, so this would be an acceptable product. And as you practice this, one thing you might practice doing is not drawing the hydrogen at the very end, or erasing the hydrogen at the end, because the hydrogens on a skeletal structure are implied, the ones on carbons, and so you don't have to draw those in. So the real product you would get from this reaction would look like this.